Hello everyone, welcome back to our adventures. In today's video, we will solve one challenge from the IdekCTF, which was last weekend. So it has a really cool reversing challenge, which I'm going to show you in this video. So the name of the challenge was Polyglot, and in this challenge, we get a single file, which is this Polyglot, which is almost 1 KB, and the description just says that there are two parts of the flag and we have to combine that and submit that. That's all there was in the description and nothing else. So if we would check what the file type is, because I don't have the file utility, I'll just look it in a hex editor, and because it is just 1 KB, so we can view it and we can see that it looks like somewhat random, and it doesn't have any like magic header at the starting. It just looks like some random hex bytes. If I would run strings on this, so we can see some strings. Well, maybe this is interesting, but like it looks garbage, and this is basically in every L file. I'm pretty sure about that. So we don't have any idea what this is, but it was in the reversing category, so it has to be some sort of shell code, bytecode, or some weird executable file. So let's try to open in Binary Ninja this polyglot file. Because it is polyglot, it might give us a hint that maybe it has multiple file formats inside of it. So when we load it in Binary Ninja, obviously it doesn't know what is the file type of it, what it is. So we can set the architecture by itself. So let's start with x86-64, because most of the architecture, most of the binaries in CTFs is basically this architecture. So we'll just set this, and let's just open this and see what we get. And it is taking a while to analyze. Any day. Okay, so it has done. So we'll get to, let's go to linear view, and we can see that first of all, the disassembly started from the 0, which means at the starting of the file itself. So we can see that it has disassembled the file correctly, and we can see that the first instruction is jump to somewhere, then there's a call to function, and we see some SSE stuff, calling some function, and again calling some function, and then there's a syscall. And this syscall actually, just to keep us from reversing, I have already reversed this during CTF, but what it basically does is, in this function, it basically sets the, initializes the matrix for RC4. This is RC4 block, and then it decrypts this data. I believe it decrypts this data. So basically it is just an RC4 encryption, and it decrypts the flag and it prints it into std out, this by this syscall, and this is the exit syscall. So all we need to do is just somehow run this and get the flag. That is one of the possible solution. And second one is, like, because we know this is RC4, we could decrypt it manually, and that's what I did during the CTF, which can be seen here. So yeah, so if you would see, like, the key is this, and this is the data, and if we would use this key and this data, let me just try to decrypt it. CyberChef. Okay, this is the data, and RC4, and the key to this, and we can get the second part of the flag. But that was not all in this video. I wanted to show another method of doing this, because we already know that from looking at the disassembly that it is already printing the flag. So why should we do this? So we just need to emulate this code somehow, and for emulating this, there is a really nice tool which is known as Unicorn. So if you don't know Unicorn, it is just a multi-architecture CPU emulator framework, and the cool thing about this is that it has bindings for Python. So we could just write some Python code and pass this bytecode into this emulator, and then we can just run it. And After the execution has completed, we can just check what is in the memory and print it. But there are some catches to it. So let's start with programming it in Unicorn. For installing Unicorn, it is basically just a pip install. So you could easily do that. Or if you would install Anger, I believe it will install it automatically. So let's start the scripting. So first of all, we will import Unicorn. We will import the whole Unicorn package. Then we will also import unicorn.x86 cons. It is basically just all of the register names and such inside of this x86 cons. Then we open our file Polyglot for reading binary and we read the bytecode. Then these are some addresses, some constants. I'll get to it later. And these are some more constants. So now this is the most important part here. Emulator is equals to UC, which is from Unicorn, and this is actually initializes the emulator, and then we have to pass the architecture and the mode. So our architecture is x86 as we have derived it, and it is in 64 bits mode because we have seen the register sizes inside, so we can conclude that it is in 64 bits mode. Then we have to allocate some memory for the emulator. We can use the emulator.map function, and we can pass some address. So this address can be anything. I just chose this random looking address, which is not totally random, but I chose this address, and it can be anything. It doesn't really matter in our case. And then we have to specify the size of that memory. So I gave 2 megabytes of memory for that, just to have some more memory. Then after that, we will write our bytecode in the variable code. We have the bytecode from the Polyglot file, and we just write into the address that we just write it to the memory we just allocated using the memwrite function. Then we also need to allocate some space for the stack, because the stack needs to be at some different address than whatever address our binary is. So we will allocate some more memory using memmap, and we pass this size, this address. So it has to be different from this because the stack is at different address than our binary. So we would have to pass that. And the stack size can be anything. I gave 1 megabyte, but it can be anything. Basically, I believe in Unix it is 8 kilobytes by default, if I'm not mistaken. Then finally, what do we do is we write into register. This reg write basically means we write some value into register. So in the register RSP, we write stack plus stack size. So basically we are just pointing our RSP, the stack pointer, into the stack. And then after we have done this, we can just say emu start, which basically means start the emulation. And we have to pass the address, the start address and the end address. So the start address is where we have loaded our code, which is at the start of the adder, which is 400,000. And then we give the flag address. So flag address is 400285. So I got this flag address from here. Let's open binary ninja, and we can see that it is basically this address, the syscall. So we want to emulate just before this. Because Unicorn doesn't support syscalls, so we would have to just stop our execution here, and then we can dump our flag. As we can see that whenever we do a syswrite, RSI holds the pointer to whatever string we want to print. So RSI, in this case, RSI actually holds the flag. So we could just stop our emulation here and then print whatever is pointed by RSI. So we did the same thing. We start the emulation till we do the emulation till the flag address. Then as soon as the emulation ends, what do we need to do? We need to first do a reg read, and we read RSP. Sorry, it should be RSI. So we read RSI register, and then we pass whatever is at that address, at whatever is pointed by RSI, we pass it into memory, because RSI will be pointing to some memory address. So we need to read from that memory address. So we need use the memory, and we would have to pass first the address, which is this, and second how many bytes we need to read. So I don't know, we can just read 50 bytes. and then I stored it into part 2, and then we can just print the flag here with the part 2. So yeah, so we can just pass this and just print this. So I have copied that emulator script into my Linux VM, and you can see that it is the same script, and all I need to do is run that with Python later, and it instantly gives us a flag that we already got it from the RC4 decryption as well. So this flag actually gives us a hint of what could be our next step. So in the flag it says an arm. So the important part is actually arm. So it basically tells us that the second part of the challenge would be like disassembling this binary into an arm code. So that's what I tried to do first in the binary ninja itself. So let me open this again in binary ninja. And I tried to set this architecture to be like, because it has 4 types of arms, so I just chose this one and I tried all of them basically, but none of them worked. If we would go into linear view, these just doesn't make sense. These instructions doesn't make sense. So the next step was maybe that is actually not ARM, but it is AR64, which in some cases some people call it ARM64, which is true. But the actual name of it is AR64. But the downside was that the binary ninja doesn't support AR64. So I would have to write my own disassembler for that, which I did during the CTF, and it is in here, disassembler.py, and I used Capstone for that. So I basically just read the file, then I initialize the disassembly engine and passing it the architecture as ARM64 and the mode to be ARM, and then I just disassembled from the starting itself and printed the disassembly. So let's just run this disassembler, and it immediately prints some disassembly, which actually makes sense. So we could do it by hand, and because it is just maybe like 15 or 20 lines at max. So if you would go by statically solving it, you could see that it basically grabs some address in x0, and then it grabs some address in I believe x3. Yeah, and then what it does is it basically does an XOR from both of them. So it will grab a byte from this address, then grab a byte from x3, and then XOR it. And it also does the same thing here. In the end, it actually prints us this SVC instruction is basically a syscall in AR64 and ARM as well. So this also does is it just decrypts the flag and prints it on the standard output. So we could again use our emulator. We just need to modify some stuff, and we can do the same thing here as well. So for that, I extended my script to do this. So basically what I did was flag address is 4003C. We have to change the flag address because it is here. I got it from here. Then again, we would have to initialize our emulator for ARM64 mode. Then we do the same stuff, allocate memory. Then we write our bytecode into that memory. Then we allocate some memory for stack. Then we point our SP into the stack. And then we again do the same thing. We just start the emulation from the start of the bytecode to the flag address. And then we do the same thing. We just get whatever is at x1, because the calling convention of ARs depicts that x1 should hold whatever we want to print. So x0 will have the where to print, which will generally be a std out, and then x1 will hold the pointer to whatever we want to print. So in our case, x1 is actually pointing to the flag. And then we do the same thing. We read whatever is at x1, and then we call memread directly on that, and we pass 30 to it. So we can pass any number of bytes, but I just chose 30 for some reason, and we just print it. So I have already copied this script as well on my system, Linux system, and we can just run it here as well. And we can see that we get the second part of the flag itself as well, which is IDEC why so many arts like this. And so we could just combine both of these parts and submit this as a flag, and it was actually the correct flag. I believe in the end it was like solved by 34 teams, and it has 450 points or something like that. So it was a fun challenge. We can solve it statically, but I showed you another method to use the Unicorn engine for emulating the stuff, because it was just printing it. We just need to somehow run the code and get the flag. So that's all for the video. Thank you for watching. Keep hacking and stay awesome.